0.75 ampere. Alright, we will now see what happens when an AC is passed through an inductor. Remember, an inductor is simply a coil of wire. Now, this coil of wire is actually an inductor. Now, why is it called the inductor again? When a current grows in it, when a current goes from 0 to maximum, the coil itself is subjected to a changing magnetic flux. And that changing magnetic flux will induce an EMF in the coil, which will oppose the original cause of it. Is that right? And that's why this is called an inductor. And the inductance L is measured in henries. So inductors oppose changes in current through them. Is that right? If a current is increasing, the induced EMF will oppose that. If the current is decreasing, the self-induced EMF will oppose that. So inductors oppose changes in current through them by dropping a voltage directly proportional to the rate of change of current. Now, in accordance with Lenz's law, this induced voltage is always such a polarity as to maintain a current at its present value. The tendency of the inductor is to maintain the current at the present value. Why? Because if the current increases, the self-induced EMF will tend to decrease it. If the current decreases, the induced EMF will oppose that decrease. Therefore, the tendency is always to maintain the current at the present value. Now that is, if the current is increasing in magnitude, the induced voltage will push against the electron flow. If the current is decreasing, the polarity will reverse and push with the electrons to oppose the decrease. So an increasing current will be opposed by the induced current. A decreasing current also will be opposed by the induced current. This opposition to current, this opposition to change in current is called inductive reactance. You see, this opposition is similar to resistance offered by a resistor, but it's not really a resistance. We call it the inductive reactance, represented by XL. Now, the relationship between voltage dropped across the inductor and rate of current change through it is V equal to L di by dt. We saw that equation in the last class. Now, the figure shows an inductor of inductance L connected across an AC generator. The voltage drop across an inductor is a reaction against the change in current through it. Now remember, an AC is a continuously changing current or a continuously changing EMF. That means the inductor will be continuously opposing it. Now, therefore, the instantaneous voltage is zero whenever the instantaneous current is at a peak. When the instantaneous current is at a peak, the current is not changing. Only a changing current will produce an induced EMF. So look at this. The blue represents the EMF and the brown or the red represents the current. So the instantaneous voltage is zero. This is the instantaneous voltage zero when the instantaneous current is at a peak. Now here, the rate of change of current is zero. Momentarily, the current is stationary there. It's not changing. Now, when is the voltage maximum? The induced voltage is maximum when the current is changing at the maximum rate. When the rate of change of current is maximum, the induced voltage is maximum. And when the induced current is maximum, the induced voltage is 0. Thus, the current lags behind the voltage by 90 degrees. Now, if you notice, in the case of the capacitor, the current was leading the voltage by 90 degrees. In the case of the inductor, the current lags behind the voltage by 90 degrees. Voltage leads current by 90 degrees. So, in the diagram, if this is the current, that will be the EMF. The EMF or the voltage leads the current by 90 degrees. Now, because instantaneous power is the product of the instantaneous voltage and the instantaneous current, the power is 0 whenever the instantaneous current or the voltage is 0. Now tell me, in the case of the resistor, we said the average power or the instantaneous power is always positive, because when the current is negative, the voltage also is negative. The two multiplied will make it positive. But in the case of an inductor, the voltage and current are not in phase, and therefore the power can be positive or negative. Whenever the instantaneous current and voltage are both positive or both negative, the power is positive. Now there you have the graph for the power. The green curve represents the power. The blue represents the voltage. The brown represents the current. And the green represents the power. And you can see the power is 0 when the current is 0, when the voltage is 0. So wherever the current or voltage is 0, the power is 0. And the power is positive when both voltage and current are positive, or when both are negative. And when one is positive and the other negative, the power is negative. However, because the current and voltage waves are 90 degrees out of phase, there are times when one is positive while the other is negative, resulting in equally frequent occurrence of negative instantaneous power. Positive instantaneous power and negative instantaneous power. Now, what does negative power mean? See, normally when you talk about the power that is in a circuit, in a resistor, for example, it is actually consuming power. It is actually absorbing power from the circuit. But in an inductor, the inductor not only absorbs power, it also releases power to the circuit. So negative power means that the inductor is releasing power back to the circuit, while positive power means that it is absorbing power from the circuit. So, since the positive and negative power cycles are equal in magnitude and duration over the time, the inductor releases just as much power back to the circuit as it absorbs over a span of a complete cycle. That means the net power used by an inductor is 0. So this means that the reactance of an inductor dissipates a net energy of 0, unlike the resistance of a resistor, which dissipates energy in the form of heat. It doesn't happen in the case of an inductor. The reactance XL in ohms for any inductor is directly proportional to the frequency. You must distinguish again here. For a capacitor, the reactance is inversely proportional to the frequency. For an inductor, the inductive reactance XL is directly proportional to the frequency. And look at the equation. XL is 2 pi FL, and since 2 pi F is angular frequency omega, we can also write it as omega L. So, going back to the capacitor, X sub C is 1 over 2 pi FC, Whereas for an inductor, X sub L is 2 pi FL. Take note of these. Example 4. An inductor of inductance 10 millihenry is connected across a 10-volt generator. Calculate the reactance in the circuit and the maximum voltage and the maximum current. Well, what are the things we know? We got the ERMS is 10 volt, the frequency is 60 hertz, and the inductance is 10 millihenry. We want to calculate the reactance. The reactance X sub L is 2 pi FL. We have all these quantities, and that is 3.770. The maximum voltage, Emax, is ERMS times square root of 2. See, whenever you are told that you have a 10-volt generator, that 10 volt is the RMS value, not the peak value. So Emax is ERMS times square root 2, and ERMS is given, so the peak value of the EMF is 14.1 volts. And therefore, what is Imax? Imax is Emax divided by XL. Like Ohm's law, I equal to V over R. Here, Imax is Emax over XL, and we know both those values. So the maximum current is 3.74 ampere. Another example. A 40 millihenry inductor is placed across an AC generator that has a maximum EMF of, this time you are given Emax. Find the inductive reactance and the maximum current when the frequency is 2000 hertz. So always read the question carefully and see what is given. You got, first we calculate the inductive reactance. XL is 2 pi FL. We have all those quantities, and that will be 502.70. Imax is Emax divided by XL. Emax we know, XL we just calculated, and that will be 0.24 ampere is the maximum current. Well, that was a very simple problem. Let's now look at LCR circuit. What does LCR stands for? We have an inductor, capacitor, and a resistor all combined in one circuit, an LCR circuit. You know by now that in a pure resistor circuit, voltage and current are in phase. In a